I've talked about some of the metrics I love. Theo, you've got a way to do disk I/O latency monitoring. It would be neat for a demo.
I can show latencies. I'm not sure I can show the disk ones, but I can show a lot of other ones.
Okay.
Database and network, things like that. Big laptop.
Yeah, I wish I was carrying that one around. It'd be easy.
It's grass. Where's my screen? Mirrored. Small. All right. Okay. So what we were talking about before was collecting latency information. So this this is latency on a database, and I can't seem to. No, I need a wider screen.
That looks awesome. That heat map is great.
Come on.
This is Windows size.
What's that?
Under arrangement, you stop mirroring the people.
I see.
You just have to shove it over to the other side.
All right. Is there a way to
Drag it.
make
Drag what
it
you
make
want
it
to show there.
good?
It's the best for display.
I don't want the best. I want the right one. Let's see. All right. Let's see if this works. There we go. That's better. All right. So this is a database where we're pulling data. Let's see, inputs. Yeah. So these are writes into the database. So every single IOP is being stored here. And what I can look, basically there's this database that we're monitoring here is actually the database that stores the metrics that we're showing here, called Eating Your Own Dog Food. But so what it's doing is over time, each one of these pillars here is an actual histogram, which is why when I move, you can see the pop-up histograms actually change. We have basically 4 different types of information that we're writing, and we're tracking latencies on every single one of them. So if you read the fine print here, this is histogram data, numeric data, text data, and then cross-node replication for the distributed system. And what it's doing is, in I think each one of these samples is 3 hours. And what we get something there. So we had a lull in writes here, we can tell, because there's not much data. If I look at this, in this 3-hour period, there's basically, I don't know, 14,000 samples. If I look at this period, we've got 20,000 here, 25,000 here. So this is the total number of actual samples that came in. This is 100% sample rate. And then as I go up and down in the picture here, I can start to see, so right now I'm hovering around 9,000. Oh, wrong side. 1K, 900. So basically this is 900 milliseconds. So my mouse is right now between 900 milliseconds and 910 milliseconds. And it tells me exactly how many of my operations were in that range. So I had 4% were slower than that, 95% were faster than that. And as I go down, I can see that across all of the various sample points. And because it's hard to show like 18 histograms on one page, we usually split those out into separate graphs. So here we can see this is read information, and there's actually not enough information to see really beautiful histograms here, and we can start to see there's different modes in these. So there's clearly a mode here, here, and there. This one has a really long tail. That stuff's really interesting. Let's see, where's the CDN? This one not super interesting. Here we go.
I consume heat maps with disk I/O latency that's the same as this, and for disk I/O issues, it's really useful. For the exact same reason, you get to see the tail, you get to understand the distribution, outliers, and so on.
So it takes a little while to, I think, wrap your brain around what the histograms are, like what these heat maps are actually showing. So the lighter it is, the less data there is. So the darker it is, the more samples there are, right? So this is not really telling you the value of anything. So there's a little block right here that's right under 2.2, which is, in this case, is 200 milliseconds. And the darker this is, the more samples exist in that. So if I mouse over this one, we're going to see some very different information that looks much prettier because it's a lot more data. Just in this vertical line alone, I mean, there's probably 2 million samples. So 700,000, 700,000, 400,000, probably 500,000 hidden away there. And what this is actually TCP time to first byte latency on a CDN. So these are two CDN nodes. I don't know why this is this way. One in Chicago, another in Chicago, and two in Amsterdam. And they're servicing clients. So what we're doing is we're actually looking at PCAP data. We're seeing the send come in, and then we're tracing that to the first data act back after we send data back. Do a little bit of math and basically estimate the time it takes to deliver the first byte to that customer. And what we can see is very, very repeatable stuff. If you do this, if you have a large global audience or even a US audience, you will see that what you have here is not a normal distribution at all, which is why standard deviations suck and averages aren't very telling. We have basically, there is actually a huge spike right here near 0, which is all your broadband customers. Then you've got all of your people that aren't quite on broadband in the same arena, right? So these are like, when I say broadband, I mean like really broadband, like gigabit in the office type of customers. Then you've got all of your national broadband customers, you've got all of your like ADSL customers, and you've got all your mobile customers out here. Right? You can actually differentiate them all out. So this is the type of thing that we see on our disk I/O latencies as well, which is usually you have two more significant modes. You have a really sharp mode in the beginning, which is all of your out of cache, and then you've got all of your latencies that are sequential and random. So that's sending millions and millions of samples basically every time we service a TCP transaction on one of these boxes, that machine will spit out a number of microseconds latency. I mean, it gets converted into seconds here, but a number of microseconds it took to deliver the first byte. So it's, I think in this system, every 100 milliseconds, it'll just kind of belch forth a payload of like, I just did 1,200 transactions and here were their individual latencies. So.
Where in this particular example, where are these latencies measured?
These are measured on the CDN node themselves, so on the leaf node, so they're on our end. So we have other ones where you have JavaScript in the browser, where it submits back page load times, and those are getting stuck in, different graphs for that.
One of the reasons I like these specific metrics being very, very high quality is that you measure what you can affect. So that's we get a TCP SYN packet go on to take until we send the first byte.
Right.
So until they get the data, because that depends on the weight. And there's nothing you can do about how fast they can.
Well, this is actually measuring, because it's time to ACK of the first byte,
yeah.
We are seeing how far they are away.
But if they're linking to the consumers to congested, that's not your problem. They'll
Correct.
get the first byte and they're not getting it.
Right. So now, if I zoom in, you can actually see this is much more granular data, right? I mean, this is 30 minutes now. And I can start to see all the different histograms inside of those. So all of that's stored minute. You can go out to a year and look at big aggregates. You can zoom down into a minute. I'm not sure that's actually minute data. That looks like, yep, it's minute data. No, it's 2-minute data. Clever. So basically the way the system works is it looks at how many pixels you have on the screen and it decides what's the most effective bucketing to do. So composed up of 1-minute aggregates. So this allows us to see if we have a shift in mode. So if one of our modes starts to shift out or a new mode pops up, Likely it means that one of our ASs stopped being announced into the right country. So we just had a shift from like someone in the US hitting Amsterdam or someone in Europe hitting the US that shouldn't be. So we can detect all of that stuff using that. We use the same thing for disk latencies. So in this same system, I can't show you the disk latencies, but what we're doing is we're measuring every disk IOP, reads and writes. And then when we see outliers that are significant, basically at this point we turn the node off and send the disk ID to on-site operations, and they jam a new drive in there. It's running ZFS, so it resilvers itself, and then someone goes in and manually verifies and turns the box back up.
Do you have any automated processes in place for detecting the new modes or the outliers? When you say see, do you mean literally somebody looking at these things?
In the disk I/O case, we have some automated tools. I would say that they're not yet generalizable. So detecting modes is actually a really hard problem. I was really unhappy about how hard a problem that was. So you can't just count the positive derivatives. It doesn't work. You need to have domain knowledge of that. Brendan wrote a really good article about it that applies in certain problem domains.
Yeah, I don't think I've solved the problem, but I took a hard swing at it, and it's interesting. We should talk about it in the visualization section. Is multi-mode detection, because there's different ways to do it.
So it's very easy to automatically detect a change in mode, but not necessarily a change in cardinality of mode, right? So it's very easy for a computer to decide. Basically, you can normalize the entire graph, and you may want to do that logarithmically, and then you overlay them and figure out the difference in surface in intersection, right? It's just like how much of my curve is gone and does exist, right? Yeah, what's the area positive and negative on that curve? Everything needs to be normalized to the right. You usually normalize it this way, and you don't normalize it that way, and because of the way we do bucketing log linear. So we have logarithmic buckets, and within those logarithmic buckets, we do linear bucketing.
So you like 10 seconds, 100 seconds, 1,000 second buckets.
We have 2 significant digits. So yeah, so 1.1 through 9.9, and then 10 through 99, like that. So that's why, very, very interestingly, these long tails are like this big, and these are tiny little lines here because it's not linear. So I think that the real answer to that is no useful generic way of modal detection. And we have the most successful we've been at is different than your approach. We do like you use a genetic algorithm to do curve fit, to do what's that called? What's that?
Piecewise curve fit, or?
Yeah, it's basically the packing problem. So we're trying to, we basically use an algorithm to figure out what the strongest mode in the system is, weighting towards lower numbers. So if I have a mode out here and I have a mode here of equal size, the one to the left is preferred. So basically you'll always find spikes in the very beginning. So that mode and the one right here on the axis will always be found.
The reason you're leaning smaller is because you're using a log-length bucket.
Right.
Therefore, it's got a smaller area, it's more dominant.
Correct. There's more data, more granularity of data there. So then once you fit that, you discount the rest of the data tremendously, aggressively fit the curve accurately and subtract it, and then try again. And you do that until that works. It produces false modes, but it's still pretty decent. And then, so one of the first example was database gets and puts. This one is TCP network latency. And then the last example, which I always find really cool, is this is application API latency. So this is like a general service where, in fact, it's being run on the other end of smartphones. So a smartphone is going in, doing an HTTP request, and getting JSON payload back, interacting. So it's for a large online company. The red line is the average latency, which, when you look at it, is horribly useless. It's all over the place. You know that there's a problem. But when you start graphing actual latencies of that, you actually have these beautiful, this is not quite pterodactyl, but
This is great.
but this is a system thrashing problem, right? So as soon as you start, you have 2 modes. Almost all systems in computing have 2 modes. So if I look at this, I've got one one mode that stays down here. This is super fast out of cache mode. And then I've got another one where we have to go back to the database here. And as the database, as the system goes on and on and on, you can see that mode actually just move out. The center of mass of that mode moves out because the system eats itself alive, right? So all of the algorithms and the way that this system works does not scale linearly, right? It's not a constant time system. So as the system grows in size, it slows down. And the funny part of this is that each one of these things is a database reset. So there's like a new database created for each one of these things. And you can see as events, happen to be sporting events, go on, and people are playing along in the sporting events, that their service sucks more and more and more and more until the event actually dies and no one uses it anymore, and then a new event starts. I think these are basketball games. January 2nd, January 6th, these are football games. So, but when your developer, because this is the problem, is most developers see the red line. That's the type of telemetry that they have. That's the type of data that they're looking at. When they jam this stuff into MRTG or Graphite or something like that, you're getting this. And you can throw this up to a 99th percentile, you can do a median. The interesting part is that this thing right here, it's just this one, let's do that. That's 38,000 samples. There were 38,000 API calls in that 15-minute segment, probably 20 minutes. So 40,000 samples. If I gave you an average and a standard deviation, the only thing that you would learn is that your standard deviation puts you a significant population below 0, right? So clearly it's not a normal distribution, right? So we would have an average that's, I don't know, probably right here. There's a little red dot. Right here, and the distribution is probably here. So clearly it thinks we have some portion below 0. I don't know how many people here can serve API service calls in less than 0 seconds, but it's probably none of you. So we don't have a normal distribution, and anything that we do in computing, especially looking at physical systems, you never have that. You have what looks normally like a gamma distribution. So if I do, and there's a lot of argument out there to do like 99th percentile and median and 100th percentile and 0th percentile, and you come up with these like 7 numbers, and you're like, oh, I hate having averages. I now have these 7 magical numbers. And it's like, when you think about taking 40,000 data points and converting it to 1, that seems to suck, but somehow converting it to 7 seems significantly better. It's not that good, is the problem. Having 99th percentile is not enough, because sometimes what you need is 99.5 or 99.9. Sometimes you really care about 80, right? So there are really interesting things that happen inside these graphs and these distributions, especially when they're multimodal, where distilling all of the data points down to a set of 5, 10, 15 statistical aggregates is just misleading at best and damaging at worst. So
Excellent.
so
Thank
that's
you.
what we got.